Good day, ladies and gentlemen. I would like to talk to you today about the role that initiating systems can play to facilitate an integrating blast process. How advancements in technology has created new opportunities for the initiating systems, some of the challenges that we still need to overcome, and potential solutions to these challenges. During previous IMARC presentations, my colleagues has presented on Dyno's view of the connected bench. In essence, the connected bench is an integrated system between the different parts of the blasting and processing functions, where relevant data is captured throughout the process. We turn that relevant data into useful decision-making information through analysis, feed it back into the system to optimize future blast outcomes. This method of an integrated system with a feedback loop has the ability to improve the safety, quality, and operational efficiency of the mining value chain by continuously refining and optimizing the process based on the data that is received. However, I think you will agree that just capturing a lot of data and then performing analysis on it has very little value if the actual process or the tasks that is performed on the bench is not repeatable, because this just leads to a huge amount of variance that makes our prediction and optimization basically a guessing game. And as you know, variation in blasting activities occurs on a daily basis. Examples such as your holes not being drilled to plan due to practical challenges on the bench, the variation between holes at the depth that we place our primers in blast holes, the actual amount of bulk that is pumped or augered into blast holes varies between plan and actual and from hole to hole. And then, of course, based on all those variances, the interroll timing or row timing we assign to detonators sometimes does not match the actual plan. It is really in eliminating or reducing this variability where automation becomes attractive and can play a huge part. Automation can afford us the opportunity to minimize this variation that is caused by human error. It also allows for us to have accurate and repeatable measurements and data capture, which we then in turn can use to better predict the future outcomes. So if we focus on initiating systems, in order to facilitate an effective integration with the automated processes, we have to change the form factor and the way and functionality that IS products currently work. In this, we should also consider how tasks are being performed by operators on the fly. Operators do a lot of tasks on the bench that we take for granted, but that is significant in the process. For instance, inserting a detonator into a booster, lacing it up, tying the wires to a stake, checking the condition of the collar of a hole, doing measurements of the hole conditions before lowering down primers. All of these tasks has to be considered in the automation process. So one of the key challenges that we still face today is correct hole location and delay assignment, and this still creates variances in the blasting process. It is mainly caused by human error due to practical on-bench changes occurring, actually altering the plan from the actual. Examples include blast holes that are incorrectly marked. This can either occur due to the hole location that is physically changed because drilling had a geological problem, etc., had to drill somewhere else, or simply confusion of operators on big benches. Users then also assign the incorrect hole or delay to dates when they're not working with an accurate blast plan due to the above mentioned changes. It also impacts our operational efficiency. It causes delays. It's difficult sometimes to locate the correct blast holes due to missing stakes, or especially when you're on something like a contour blast. And fault finding and troubleshooting on the bench becomes difficult. Finding the one detonator that might not be working becomes difficult on big benches, as we do not know exactly where that detonator is located. Also, in the current IS process, it requires multiple visits by multiple people to each blast hole during the loading process, which can really be optimized using automation. I think it is critical to ensure that the desired time is placed into the correct detonators, as this directly influences our blast outcomes. It directly relates to fragmentation, which in turn relates to your loading efficiencies and your productivity and your downstream recovery of metals, all by assigning the correct delay time to the detonator. So in order to solve this problem, we have to look at the way that we tag in a different way. Instead of trying that the user locate or identify the correct hole, imagine a system that tells the user at which hole he is, and based on that actual position, assigns the appropriate timing delay to the detonator. In order to do this, we actually require high accuracy to pinpoint the location of the hole on a bench and to differentiate this hole from other holes on the pattern. It is here where the differential GPS technology that is integrated into your blasting control system actually adds a lot of value, as it can increase the accuracy to sub-meter. So currently in normal GPS systems, your accuracy is somewhere between 1 meter and 5 meter, which makes it difficult to pinpoint a specific blast hole on a bench. With the differential GPS, using correction from a known reference base, in real time communicating to your tagging advice, you can actually pinpoint the location of the hole and the detonator you're busy using. So this also creates opportunity for the integration with the blast design software, as it affords you now to do simulations at the design and after loading, due to the fact that the system can actually highlight discrepancies between what you actually planned and what was actually drilled, giving you the opportunity to tweak your timing to achieve the optimal blast outcomes. Also, in instances where drill rig data is not available, this system can be used to actually give you the hole positions and thereby creating the blast plan based on actual positions. Due to the fact that if you look at the system now, that the timing is assigned based on the actual hole location, no input is required from the user anymore. And tagging can be done in any order on the bench, because the timing of the detonator is now assigned based on location, not a tagging path anymore. So the step of automatic hole detection and then the automated assigning of delay times increases the repeatability by removing human error from the tagging process. And that is what we are really after. It also addresses operational efficiencies, as it caters for multiple users or machines to tag at the same time on the bench, and they can do this in any sequence. Due to the fact, as I mentioned, that timing is not assigned by a tagging path, but by the actual location. Another key feature and benefit is the fact that we now know the physical location of each detonator on the bench. The system has the ability to direct either users or machines to a faulty detonator, which significantly will reduce the time to fault find on a bench and affords the opportunity to perform remedial action. This technology also offers flexibility, as this differential GPS module is not only used in the initiating systems, but can be placed on your MPUs, drill rigs, or the IS automated loader, hence connecting all of these pieces of equipment on the connected bench. So the ability to repeatably tag and assign the delay timing correctly, removing human error, and the fact that this can be done in an automated fashion by actually using hole location to tag the timing into the detonator is a key building block in a move to a fully autonomous IS loading system. So now that we've looked at the variability of delay timing and hole location on a bench and sort of say, yeah, there's a solution to solve that, the next variable in the system is in the IS primer location and the hole conditions. As mentioned earlier, this can be solved by utilizing an automated machine or an automated process to actually measure the hole conditions and deploy the initiating system down the hole. However, one of the big challenges remains the interconnection between holes of the detonating systems in their current form factor. First of all, it is difficult to automate this with repeatable and reliable connections on surface. And secondly, if you could get that right, you're still susceptible to damage on surface with moving machines, etc., because of the wire infrastructure that is deployed on the surface. So a potential solution to resolve this is the removal of those inter-hole connections, and this is where wireless detonators start playing a role. So one form of a wireless detonator is a unit that uses through-the-earth communication. It's a one-way communication. It happens at a very low frequency and low speed. I'm talking through the rock, but the unit has no wires. This really creates a good opportunity for alternative mining methods, as there is no in-hole infrastructure like wires. It affords the opportunity to load blast in a single pass. However, you don't have to then take that whole blast. You can take the blast in different sections without causing damage to units that is earmarked to only be initiated at a later stage. Obviously, because this unit does not have no wires or no interconnection on surface to it, it is well suited to automation. And because the unit is an integrated system where your detonator and booster is basically one product once you've screwed it together, it fits the ease of automation, makes the ease of assembling the detonator into the primer quite easy, and it resolves that problem. I think one should also just note that with all these opportunities, the system also comes with some challenges that we need to consider. One of these challenges is the fact that we only have one-way communication to the unit. This really means that we cannot test during deployment or after deployment, which could influence reliability, and it also limits the amount of information we can provide as feedback to both the user or a machine into future. A second consideration is that due to the fact that you only have one-way communication, once you've timed the detonator and deployed it down the hole, you cannot change this timing. So you actually lose flexibility in reassigning time to the detonator. And this is necessary, as I mentioned earlier, when changes on the bench has occurred. So your drill patterns has changed, and now you want to change the timing to actually suit that, to optimize the blast. That benefit has been lost. Also with this technology, due to the inherent technology of coupling magnetically, the form factor of the unit is quite big. So the physical size constrained it to be used in all applications, specifically applications where there's smaller diameter holes. And then a key point is that you still require a mechanism to place this detonator at the correct depth in a hole. So you can't just drop it in downhole applications specifically, but you need to lower it to the correct depth and keep it there. So even though this product affords some innovative opportunities and solves some of our automation concerns, and really has the ability to change the way some of the mining applications, it also introduces some uncertainty and variability into the process that we need to manage. One alternative to the full wireless system I just explained is a wireless from the collar unit. A unit like this basically communicates wirelessly from the collar of the unit, from the collar of a hole to other units, and will greatly assist with automation deployment of the initiating system as you have removed the interhole connections. Once you communicate wirelessly at the collar of the hole and not trying to communicate through the earth anymore, you overcome one of the technical burdens of communication and brings you back to the ability to have a full bidirectional communication system. As soon as we have a full bidirectional communication system, it makes continuous testing and deployment possible again, brings back the flexibility that you can change your time subsequent to deploying the unit down the hole. And another key benefit of this is that you utilize the standard electronic detonator form in the market now. This affords users the opportunities to use standard initiating system as accessories with it, like Stinger boosters. It also gives you the same reliability and shock hardness as current detonator products. However, the biggest benefit of this is the bidirectional communication and the fact that there is no interhole connections, and that makes this product well suited for automation. The challenge of getting the primer to the correct depth in the hole is the same as for a unidirectional wireless dead or current wired electronic deads in the industry. That still has to be solved through an automated process. The solution, when we look at challenges, will not be able to do all the niche mining applications that is covered by the unidirectional detonator due to the fact that you do still have a downline infrastructure. However, for most other applications, it affords communication and flexibility, assisting with our aim, which is to increase reliability and predictability. I think it is fair to say, as is the case now, one still has to match the required product to the required application, and I don't think that changes into the future. With the development of the wireless and hybrid detonators, a hybrid detonator be a combination of the shock tube and electronic detonator, we have solved the fundamental change in the detonator has actually occurred. and that is namely that the energy source is now safely integrated as part of the detonator. In the past, your energy source was separate from the detonator. In these new products, you actually have an energy source that has been safely integrated with your product. This increase in the available energy budget now, in combination with the lower cost and more freely availability of integrated sensors, which has come about due to a drive to move to big data, actually creates a unique opportunity for initiating systems. Effectively, you can now imagine that each initiator in a whole becomes a sensor for measuring conditions such as temperature, the density of the bulk product you are in, etc. The units can also become geospatially aware. And what I mean with that is not only does the detonator know where it is in a hole, but it knows where it is in a hole relative to other detonators. If we consider this detonator now as a sensor and the amount of data that has been gathered and passed into the digital platform, all this data affords the opportunity in future to move to the possibility to utilize artificial intelligence for modeling and designing blast timing. So basically, you have a sensor in every hole, getting the granularity of the data that feeds better, that can be put into a process to optimize the blasting design and timing. What I would like to say is I think that the journey from where we are today to the connected bench and all the changes and adoptions that has to come with alternative initiating systems does not occur overnight. Hence, it is really important to recognize and plan for the fact that a one size does not fit all when it comes to initiating system. And as I mentioned earlier, the correct technology must still be chosen for the correct application. At Dyno, we really believe that creating a centralized system for initiation control, linking to the digital platform, is key to the success of a connected bench. The reason for this is the system must be able to accommodate current and future initiating system products, with the understanding that obviously the different initiating system products that you hang off the centralized control will have different data gathering capabilities into the future. Once we have all this data of both existing and future initiating systems in the digital platform, it is also critical that the data that we have obtained is open to third-party integration. This is necessary to truly facilitate a connected bench between all the other functions in the blasting process. A centralized control system really provides us with the following benefits, if we think about it. The fact that you have real-time available and continuous communication between your central control and your blasting points means that changes and alterations to the blast can be made in real time as you realize that conditions has changed. So changes to timing and charging. It also affords the opportunity for remedial action before blast time. A centralized control of initiating systems also means that if you take blasts in different sections or areas of the mine, be that surface or underground, one can control the safety and security by geofencing personnel and equipment, but you can also try control the seismicity of events by timing these different areas of blasts together. It also optimizes efficiency by being able to do multiple blasts basically in one blast window. Another big benefit of centralized control is management information. Automatic blast logs and inventory reports can be generated and passed straight into the mine management information system. And then, of course, our overall goal, which is blast optimization through reliable data modeling, is key. So in conclusion, what I try to show today is that in the initiating system technology world, key technology blocks has been designed to minimize the variability in the blasting process. These blocks have been developed with a phased approach in mind so that you can use them standalone in current products now or fully integrate the solution into an automated and connective bench into the future. The end goal is really to use reliable and predictable data to enhance the mining value chain efficiency into the future, and initiating systems has an important role to play there. I would like to thank you for your time.